Hello, math scholars, coming at you with another 4.4 day 2 math lesson. Pretty excited to be here. It's a Wednesday. Hope you're having a happy day. Make sure when you watch the video you comment and like and subscribe. We're excited to learn math. Woo! I think I've got like 12 subscribers. We're halfway to 24. All right, we're going to start off with what you are allowed to cancel when it comes to logarithms. So just like 3 minutes ago, we were talking with Spencer about a math problem that looked like this. And I said to Spencer that yesterday, that was a 2, yesterday we said that 4 to the first power would equal 4. And if 4 to the first power equals 4, all of this stuff that I'm circling has a value of 1. Because 4 to the first power equals 4. So really what you're allowed to do is just slash it off because it has a value of 1 and just have that everything else that's left is your solution. So this homework problem last night had the solution of 2/3. So that comes true at any time that you have a matching base here and a matching number here. You can just slash it out and have whatever's remaining as your solution. All right, you want to see another example? I'm getting weird looks. Let's say it's log 10 of 10 to the 5. This 10 and this 10 here, you can just cancel out because 10 to the first power is 10, has a value of 1, and my final answer would just be a 5. Okay. The second one, this is more awkward because now you have a base, and then in the exponent position, you have a log. Very strange. But if you have a base and then you have a log of that same base, you can slash it out, same deal, and just have whatever is remaining be your answer. So I'll just make up an example. How about 6 to the log base 6 of 5? So since I have a 6 and then I have a log 6, I can slash all that out, and my final solution would just be a 5. It's just kind of how it works when the log is in the exponent position. You want to see a couple more examples? Sometimes the examples clear it up. Let's try this sample right here. Yesterday we learned not all logarithms will actually have their bases visible. They're little tiny numbers. If you do not visually see a little tiny number, what number is it? No, it's a 10. It's a 10, not a 1. Okay. So what we have here is definitely a cancellation thing. Since you have a 10 and then the exponent position, you've got a log 10, you can cancel and just say that your answer is the 4. So that's all that would remain after you cancel the 10 log 10. All right, am I allowed to cancel this log 5, 25? Cancel like that? No, because the 25 and the 5 don't match. But we can rewrite the 25 to make it something we can cancel. 25 can be rewritten as 5 squared, right? Let's go ahead and do that. Let's rewrite 25 as 5 squared. Now we still kind of would have that x hanging out, right? And if I have a 2 on the inside of the parentheses and an x on the outside of the parentheses, and I want to make it one term, those two would multiply. So we'd have log 5 of 5 to the 2x, and now we can utilize the cancel property. Log base 5 of 5 can cancel, leaving me with the final answer of 2x. You want to try the next one by yourself? Actually, I'll go ahead and pause the video, and I want everybody to try the next two all by themselves, and then restart the video when you're ready to check. All right, go ahead and check that you got x on number 10 and negative 3x on number 11 because of what you canceled out. Oh, this will be a good one. Let's do this one together so I can talk to Marty about it. See that 64? 64 doesn't match the 2. So unfortunately, I can't utilize any cancel property at this time. But we could probably rewrite 64. Use your calculator to experiment 2 to what exponent would be 64. Like, is it 2 to the 4th? Is it 2 to the 5th? Is it 2 to the 6th? It is 6. Good job. I think Lexi figured it out. So we're going to rewrite 64 as 2 to the 6th. We still have that x up front. So now I'm going to take that 6 and the x and make it 6x. Does that make sense? So we'll have log base 2 of 2 to the 6x. Cancel property. And we have a 6x. Verify. I'm going to click pause and I want everybody to try 13. Alright, so we had a scholar come forward and tell us that ln has a base of e, and that allowed her to cancel all that, leaving her with the answer of 20. Now we did have the discussion with someone else in the room that you could probably just type it in and it would probably give you 20 if you typed it in correctly. Alright, let's move on to finding inverses. So to find an inverse of an equation, it doesn't matter if the equation's a parabola, an exponential, a logarithmic, a straight line. There's a few steps you need to follow, and it goes like this. I have a song. Switch the x and y, then resolve it. Have you heard the song before?
Yes.
Good. My last class said they had never heard the song, and I swore I had taught it this year. So you switch the x and y, then resolve it. Those are your 2 steps you follow if you want to find an inverse. Now what's cool about these is if you start with an exponential, like we are going to do on this one, your inverse will be a logarithmic. So exponentials and logarithmics are inverses of each other. It's super cool. You ready to try it? All right, sing me the song. That was so great. I hope the microphone caught that. So we're going to switch our x and y. Now, if you truly like doing left, right, center techniques, this is probably awkward to you because normally the base and the exponent are on this side of the equal sign. So just arrange it the way that you're most comfortable with. That's how I'm most comfortable. And now we're going to solve for y by putting this in logarithmic form. So we're going to write log. We're going to leave us a big space. We're going to write an equal sign. And then we're going to do a quick left, right, center. So this 6 is my base. He goes on the left. This y is my exponent. He goes on the right. And this x is my answer, so he will go in the center. Left to the right equals center. And just like magic, look at that. We're now solved for y. Y is all by himself, which is the definition of being solved for y. So that's our answer. So fun. We love it. We'll do another one together because I know it's weird. All right. And this just tells you what I had told you verbally, so if you want to jot down what I have at the top, you can. Logs and exponentials are inverses. And this just kind of explains if you start with an exponential, you end with a log. Yeah? Yeah, log base 6 of x equals y. Did you see that? The box came out from the answer. That was crazy. All right. All right, we are on our next problem. We need to find the inverse, so we're going to switch the x and y, then resolve it. Who's your little guy that's living right there that Carly taught you about? Yep. So let's go ahead and perform our switch. So when I switch my x and y, this is what it looks like. I like to write the e there just to remind my students that it is there, even though you can't normally see it, it's invisible. So there's my switch the x and y step. Now I have to do my resolve, and we're solving for y. Again, if you're a left, right, center person, this probably looks awkward to you because normally you have your equal sign over here. So go ahead and rewrite it if that helps you perform your left, right, center easier. So to do my left, right, center, my e is on my left, so he's my base. My x is on my right, he's the exponent. And my y plus 3 is in the center, so he's my answer. Now I'm resolving for y, so I still have one more step. Do you know what it is? Awesome. And then you're done. So our original was a logarithmic, and our inverse now is an exponential. Well, thank you for the round of applause. No. He was clapping because he thought we were done with the lesson. Not quite. We have some graphing to do. Graphing. We will end the lesson after we do 2 graphing problems, so however long it takes. So let's talk graphing. Can you all get your graphing arms ready? Check them out. Show me with your arms exponential growth. Should be growing. Show me exponential decay. It should be decaying. Now make sure this arm isn't going like this. I see some people with their arm down here. What's wrong with that? Exponential decay never goes below this guy. What's this guy called? The asymptote. Right. So now I'm here to tell you that exponential growth and decay curves are inverses of logarithmic curves. So if this is an exponential growth curve, I'll label it growth, then I will flip it over the inverse line. The inverse line is line y equals x. And this is what a logarithmic growth would look, or a logarithmic graph would look like. So it's also going to have an asymptote, but guess where its asymptote is? This guy. Yes, that's what we're going to explore here. So I do have a slide to show you. I don't know if you want to write it down or just look at it. I'll pause the video real quick. All right, we're back and we're going to make a table together, make a graph together with our calculators, and then label the asymptote and answer a question about what the domain and the range is. Move this out of our way. So let's pull up our calculators. Everybody except Lexi has a TI-84, right? Okay, so Lexi and Spencer are my TI-83 people. Everybody else, you're going to have that special log button. So I'm going to need you to grab that log button by doing math, up, up. And then since you have that special button, you can make the base of 3. Because again, if we use the log button on the calculator, I don't know why my 3 is not pushing. There we go, 3 and x. If we use the log button that's on the calculator right here, it would have a base of 10, and that would be bad. So Lexi Spencer, you're probably wondering what you will enter in your graph. You will do log x on the top, like that, and log 3 on the bottom, like that. And by doing it that way, you can use the base 10 and have the same overall effect as us using the base 3. Yep. Yep, and then close that parenthesis. You got it? Perfect. That looks okay. Alright, let's fill out our table. You might be surprised at what you see on the table when you go into table. Second table, you're going to see a bunch of errors because you cannot take the log of a negative. You can have a negative here, and you cannot take the log of 0. So we're going to have error all the way through to 0. Now when we get down to 1, we should start to get numbers. At 1, we're at 0. And can I just have somebody just read these off so I don't have to toggle back and forth? So 0. At 2, what do you have? 0.63. 0.63. And at 3, what did you get? Okay. And then you can go ahead and hit graph and see what it looks like. Yep. Pause this up. Help. Alright, we're going to go ahead and click graph, and I have to tell you something strange about the graph. When you click graph, it kind of looks like it stops right here. It actually continues skirting along that y-axis all the way down. So I'll go ahead and draw it on the board, like it is what I'm trying to tell you. So it crosses through at 1, 0, and it just kind of continues down forever, because that will affect the rate, knowing that it continues down forever. So we do have that asymptote I spoke about a few minutes ago. The asymptote is the y-axis, which is the equation x equals 0. Now let's just look at the graph very carefully to figure out domain and range. Where's this graph traveling left and right? It's traveling from 0 to infinity, not including 0 though. You can't actually get to 0 because of the asymptote. And then range is going to be all reals because it can go up and down. Do you want to know something cool? Remember last week we did exponential growth and decay? They just had a domain and range that were reversed. That's how inverses work. It reverses the domain and range because it reverses the x and y's, you know? Okay. All right, we have one more graph we can call it a day. We're going to do one that has done a little bit of shifting. It is this one. So I'll go ahead and talk you through the shift questions. This graph has translated. This is our left-right number. So it's 3 units to the left. It's in parentheses, so it's opposite of what you would guess. You would probably guess right, but it's left. and then it is shifted 1 unit up. Now, is it the left-right shift or the up-down shift that's going to move our asymptote?
Okay.
It's the left, because our asymptote nowadays is this guy.
Oh, no.
So it's going to shift 3 left. So before I even start, I can draw my asymptote in. It's opposite from last week. Last week, it was the up-down number that shifted our asymptote, because last week, our graphs looked like this, and our asymptotes were horizontal. Does that make sense?
Yeah.
So that's why up-down shift. This week, our asymptotes are vertical, and our graphs look like this. There's the right left shift on the day.
I was just a little put down.
Oh, okay. Alright. Alright, we're going to read down our table of values. We only have one error this time. Does everybody else have 1, and then 2, and then 2.6? No? I rounded it. 3, 3.3, and I think 3.5 was the last entry? You didn't get it? Alright, I'll come look. Alright, so just to finish this up, if you click graph, you should see it's an exponential growth graph. But this time, I'm just going to do the rough sketch, not to make it perfect. We're running short on time. It's going to look like this. Your asymptote has moved. We already discussed that. It's at -3. Your domain would be -3 to infinity. And then your range will be all real numbers. So that kind of completes that. I'll leave this slide up because I know people are probably still writing. I'll even pause it here. The homework is in the book. It's over on this board. So make sure you snap a picture of it or write down. Okay.
Uh-oh.